En este tema
In this lesson we study the homogeneous systems of linear equations.
de ecuaciones lineales. Como sabéis,
As you know, a system of equations is said to be homogeneous when the independent terms are all null.
entonces,
Then, in the top part of this transparency you have an homogeneous system of equations. This system consists of some coefficients, which are the coefficients, that multiply a series of unknowns. What are x's? In this case we consider n unknowns and m equations. We must keep in mind that the number of equations, and the number of unknowns does not have to coincide. Since we are dealing with the orthogonality concept, and we have seen the orthogonalization algorithm, and I've promised that all the problems will be solved with this algorithm, that is what we are going to do. For this, we have to see this system in another way, that is, we would have to put on a kind of orthogonality glasses, to see this system in a different way, and that's what you have in the lower part of the transparency. There we have written a vector that is the a1 1, a1 2, a1 n, multiplied scalarly by another vector, which is x1 x2 xn, the vector of the unknowns, and that scalar product is equal to 0. As you know, if the basis is self-standardized, the scalar product of those two vectors would be a 1 1, times x1, plus a 1 2, times x2, plus points, plus a 1 n, times xn, which is precisely the first equation above. Analogously, we could write the other equations, such as scalar products of the vectors of the coefficients of each equation, by the vector of the unknowns equal to 0, and so, all of them. So, what I want that you see clearly, is that the system above, it's exactly the system below, they express the same conditions and, therefore, they have the same solutions. But the system down is telling us something very interesting. What it is saying is that we are looking for a vector of unknowns x1 x2 xn, perpendicular to all row vectors of the coefficients, that is, what is saying is that the solution of this system is the subspace orthogonal to the subspace generated by the row vectors of the coefficients of the system of equations. So, notice that this idea, this way of looking at the system, immediately tells us how to solve it. It tells us, first that the system is a linear subspace, and in second place, since it is orthogonal to the subspace generated by the row vectors, it tells us that what we have to do is to apply the algorithm, and get its orthogonal space. That is the great contribution of the orthogonality. Let's see an example. Imagine that you have the system that appears in the transparency above. It is a system of 4 equations with 4 unknowns, so, what we have to do, as we have already seen in the previous transparency, is to calculate the orthogonal space to the subspace generated by the vectors of the coefficients of the equations. So, what we do is, first equation, the coefficient of x1 is 0, the coefficient of x2 is 1, the coefficient of x3 is -1, and the coefficient of x4 is 2, then the vector is the 0 1 -1 2, which is the vector that we enter as the first vector in our algorithm. Then, we calculate the scalar products, starting of course from the identity matrix, and pivot. Next, you have to enter the second vector. Let's go to the second equation and see that the coefficients of x1, x2, x3, x4, are. They are 1 1 1 and 0. Therefore, we enter the vector a2 in the algorithm, we pivot, in this case with the first column. Previously, we had done it with the second, since we had not been able to pivot with the first. So, we get the transformed matrix, which appears in iteration 3. Next, let's go to the third equation, we look at the coefficients of x1, x2, x3, x4, and we see that they are 1 2 0 1, which is the vector that we enter in iteration 3. Next, we pivot, and we go to the last equation, which is x1 plus x2 plus x4, and the coefficients of your unknowns are 1 1 0 1. Then, in the last iteration, we enter the 1 1 0 1, we pivot with the vector that is in the third position, in column 3, and we get the final table, which appears there. So, look, the orthogonal subspace is obtained eliminating the column vectors W, with which we have pivoted. As we have pivoted with the 4, we eliminated all. This means that the only vector that satisfies the system is the vector 0 0 0 0. Therefore, this system of equations, which we have selected, has only the null solution, the null vector x1 x2 x3 x4, equal to the 0 vector. It should be noted that all the homogeneous systems have this solution, because obviously, if all the values of the unknowns are null, when operating and calculating the products by coefficients and adding, what we get is a 0. That is always true. We're going to do something, which is also very suggestive. What I'm going to explain to you is that with the last matrix, that we have obtained in the previous transparency, we will be able to solve not only the system of equations that they have given us, which in this case has as unique solution the 0 vector, but we will be able to solve any subsystem of that given system, for example, with the solution of the third, or the fourth, or the second, or of the first, third and the fourth equations, or of the second, the first and the third, or any subset you want. So, let's go to see that with very little effort, that has been to not eliminate the pivot vectors in our pivot operation, because we could have eliminated them to get the orthogonal. We have them maintained, and at the end, we have obtained a matrix 4 by 4, which is what you have there on top, where the final table is. So, let's assume that we want to calculate the solution of the last equation alone, which is what you have in the table, in the second row, x1 plus x2 plus x4 equal to 0. So, if we want to solve that system, the only thing we have to do is, in the final table we have to eliminate the columns with which we pivoted when we introduced this vector 1 1 0 1, which is that of the coefficients. Then, that column is the one that has heading W4, the index that appears in the final table. It tells us with which column we were pivoting in our previous process. Then, to pivot, in the case of the last equation, we did it with the third column, which is where the heading is W4. If we eliminate that column, the subspace orthogonal to the one generated by the coefficients of the other equations, is the one generated by the other three columns. You have them there, all three first. Then, to the right of the equation, in the table where it says solution, you have that x1 x2 x3 x4, which is the vector of the unknowns, the solution, in which some row 1, row 2, row 3 coefficients, which are the coefficients that we are going to use for linear combinations, and they appear some vectors that are precisely those three columns that resulted from eliminating that equation. Therefore, the solution of the equation x1 plus x2 plus x4 equal to 0, it is a subspace vector of dimension 3, since three vectors appear, which by the way are a basis, because in the algorithm that we use, we always get bases, and they are those that you have there, the vectors -1021, -1011, and 01 1 1. Look how interesting. Although our primary intention was to solve a system of 4 equations, we have been able to solve the case of this equation. Let's suppose now that what we want to do is to solve the last 2 equations, solve a system with only the last 2 equations. So, what we do is we go to the final table above on the right, and we look for the third and fourth equations, with what columns we have pivoted, and we have pivoted, as you can see, with the last 2, because the W3 and W4 appear in the last 2 columns. We now eliminate those 2 columns, and we have 2 columns left. Well, the solution you have there, in the system of these 2 equations, it tells us that the vector x1 x2 x3 x4, is equal to the linear combinations of 2 vectors that are precisely, these 2 that have remained after the elimination. Therefore, the solution is that subspace of dimension 2. Finally, if you want to solve the final system, which is the system generated by the first, the third, and the fourth, that you have there, we eliminate in the final table, the columns W1, W3 and W4, and we only have the W2. So, we see that the solution, as shown in the table, is that x1, x2, x3, x4, is equal to rho 1 by the vector minus 1, 0, 2, 1, which is precisely this vector, which results after eliminating the other columns. Therefore, what the algorithm of the orthogonality is, first of all, a new way of viewing homogeneous systems, instead of seeing them as a linear combination of the unknowns equal to 0, they are some scalar products of the unknown vector by the row vectors of the coefficients of the equations equal to 0, which are reflecting a concept of orthogonality. The vectors that carry components, which they have the coefficients as components of the equations, they are perpendicular to the solution vectors and, therefore, the subspace solution matches the subspace orthogonal to these vectors. Finally, we must say what we understand by equation of a subspace. We have seen that a homogeneous system of equations is equivalent to a subspace and, therefore, we can say that all subspaces can be expressed through homogeneous systems of equations, which are called the subspace equations, that is, the set of conditions that must met by the components of their vectors so that they belong to the subspace. It should also be noted that the subspace orthogonal to the subspace is the subspace generated by the vectors of the coefficients of the equations of the system. That is important, and it turns out of the first transparency, where we have seen this equivalence. It is also appropriate to indicate that the homogeneous system that they give us, may not be in minimal form, that is, can have equations such that some are linear combinations of others, which means that they are redundant, that they could be left over, and they can be eliminated. To eliminate these equations, what we can do is to use our algorithm, with the method that we described when we studied the range. We can also get it, if given a homogeneous system by your equations, you want a basis, just get the subspace orthogonal to that of the coefficients, through the algorithm, obtaining the required basis. So, as a conclusion of this lesson, we can say that the orthogonality has allowed us to see the problem of homogeneous systems from a very different way, and a very rich, since it allows us to solve all possible subsystems of a given system. It has also allowed us also interpret in a clear way what are the equations of a subspace.
Todos los subsistemas posibles de un sistema. Y además nos ha permitido también interpretar de una forma clara lo que son las ecuaciones de un subespacio.